Okay, AP Calculus, AB 6-5 office hours. This is a book assignment. Should have tried all these problems. Check your hours in the back of the book. I'll go over the evens as I go over the assignment today. So a lot of this was, a lot of the first problems were just drawing pictures. It says in each part sketch the graph of the function f with the stated properties and discuss the signs of f prime and f double prime. So part A was a function that is concave up, which means that f double prime is positive. So they said to discuss that, and it said that it's also increasing. So it'd be f prime of x is positive on the interval negative infinity to positive infinity. So you got to draw a picture that kind of matches this. So it's got to be concave up and increasing. So something kind of like that. It's increasing, it's going up the whole time, and it is concave up. Part B said that we want a function that's concave down, which means f double prime is negative. That's something that you're supposed to put in your answer. It says to discuss the signs of f prime and f double prime, and it is increasing. So that would be f prime is positive on the interval negative infinity to positive infinity. So it's concave down the whole time, but increasing. So it's going up left to right, but it's concave down. So that's how that would look. C, let's see, function is concave up and decreasing. So concave up, f double prime is positive, and decreasing. So f prime is negative on negative infinity, positive infinity. So the graph, it's concave up and decreasing. Concave up and decreasing will look something like this. It's going down, but it's curved upwards. And then D says function is concave down and decreasing. So concave down. So f double prime is negative. And it is also decreasing. So f prime is negative on the interval negative infinity to positive infinity. So a quick sketch of that would be it's decreasing and concave down. So something like this. So it's going down left to right, and it's also curved downwards. So that's what you were doing, number one. Number two, similar problems. A says that it's each square sketch graph of the function f with stated properties. So these ones I think are a little more complicated. So it's increasing from negative infinity to positive infinity, and it has an inflection point at the origin, inflection point at 0, 0, and it is concave up from 0 to positive infinity. So what would that graph look like? Well, it has an inflection point here, right? And it's concave up. It's increasing the whole time. It's concave up on the right side, and if it's a flex point, it means it has to be concave down. So this is what it's going to look like. So f double prime is positive, f double prime is negative, f prime is positive the whole time, f double prime right here is 0. So you get an inflection point. So something like that. B says it's increasing from negative infinity to positive infinity. And it says as an inflection point at the origin, IP at 0, 0. And then it says it's concave down on 0 to positive infinity. So similar, sounds very similar. So we definitely have an inflection point here, and then it's concave down from 0 to positive infinity, but the whole graph is increasing, right? So it's got to, then you got to switch it. So something like that. F double prime is positive, F double prime is negative, the whole F prime is positive the whole time, F double prime is going to be 0 there, the inflection point. Okay, C says it's decreasing on negative infinity, positive infinity, and has inflection point at the origin, IP at 0, 0, and it's concave up on 0 to positive infinity. So inflection point here. So I'd probably say F double prime is 0 there. Now the graph is decreasing. It's going to be going down left to right, but it's concave up from 0 to positive infinity. So it's decreasing, it's concave up. So it's going to look like that. And then it's got to be concave down if you had a inflection point. Concavity has a change. And F prime is negative the whole way. D, decreasing on negative infinity, positive infinity. And inflection point at the origin, 0, 0. And it is concave down on 0 to positive infinity. Okay, so it's decreasing all the time, but it's concave down here, so it's got to be concave up here. So F prime is negative the whole time, but here F double prime is positive, F double prime is negative. So something like that. So just trying to help you get kind of used to the basics and be able to just draw some pictures of these. 3 says, 3, they give you a graph. It says use the graph of the equation and the accompanying figure to find the sines of dy dx and the second derivative at the points A, B, and C. So the picture, I'm just going to recreate the picture real quick, which you might also do on your own paper. It's really how you're going to show your work. It kind of looks like this. Pretty basic. It's got some points, B, C, A. And they say that it says find the sines of dy dx at the points A, B, and C. So point A, the slope is negative, so dy dx is negative. It's concave up, so the second derivative is positive. Point B has positive slope, dy dx is positive, and it's concave down, so the second derivative is negative. At point C, slope is negative, so dy dx is negative, and the second derivative, it's concave down, is negative. So there you go. It's a quick little analysis of that graph. 5 says use the graph of f double prime and the accompanying figure to determine the x-coordinates of all the inflection points. Okay, so they're giving you a graph of the second derivative. You got to read the directions because people are going to answer this one way wrong. This is going to happen on tests in my class too. You're going to answer it way wrong because they're not really thinking about what they're being given. So there's this graph that looks like this. So let's make one. Okay, so there's this graph, and they want to know what are the inflection points and explain your reasoning. So I'm looking for inflection points. Now, some people are going to be like, oh, this is an inflection point, and this is an inflection point because it's changing concavity. No, this is the second derivative. This is the second derivative already. So this is where f double prime is positive, and f double prime is negative, and f double prime is positive, and f double prime is negative, and f double prime is positive. And whenever concavity changes, and f double prime change signs, you get inflection points. So you get one here, 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 and here. So we have inflection points at x equals -1, 0, 1, and 2. The reason is since f double prime of x changes signs at each of these points. Changes direction, each of these points. So something like that. Okay, number 7 says to use the graph of in the company figure to find the requested information. So kind of similar thing. They give you a picture of a graph. I'm going to sketch it real quick. And okay, so seems like there's a point here, and a point like here, and then a point down here, and a point. So there's usually a point lined up with each of the x values here. I'm just trying to do a quick sketch of this. Something like this, and it kind of looks like that. Something like that. Okay. So A, it says find the intervals in which f is increasing. So this is kind of like what we did in class. So we're going to say 4 to 6, and we include the endpoints. 4 to 6, it is increasing. That's the only place. That's the only chunk. 4 to 6. B, where is it decreasing? Well, it's decreasing from 1 to 4, including the endpoints, and 6 to 7. And C, where is it concave up? Well, it's concave up here, and then it's concave down, and then it's up here, and it's down. So it's up from 1 to 2, parentheses, and 3 to 5. D is concave down. And so concave down is 2 to 3 and 5 to 7. And E says inflection point. So we want all the inflection points, location. So that's where it changes concavity. And so it changes at 2, 3, and 5. 2, 3, and 5. All right. That's going to be a good chunk of points on our next test. It's just looking at pictures and identifying things. Okay, 11. He's asking you to do a bunch of different stuff. So these ones say find the intervals on which f is increasing, decreasing, concave up, concave down, and inflection points. So the same questions as 7, but without a picture. So this is where we're going to do a bunch of line checks here. So the first thing you do is to find the derivative. 2x minus 5 is set equal to 0 undefined, right? And then that's going to be x equals 5 halves is a critical point. So we're going to do a line check, label it, put this on here, not an open or closed dot, just a mark. Test something. We could test 3, positive, negative. So I like to draw these little arrows. This is where it's decreasing, increasing, relative min, critical point, lots of good stuff from this. So they said, where is it increasing? For part A, it's increasing on the interval 5 halves to positive infinity. And you include the 5 halves. B, use the same word for decreasing. So it's decreasing on the interval negative infinity to 5 halves. So those are those answers. So f double prime It's going to help you find concavity. So that's going to be 2, which never equals 0 undefined, which means we're not going to, I mean, we could show a line check, but it's positive all the time no matter what. It is always concave up. So C says, when is it concave up? Well, everywhere, all reals, negative infinity, positive infinity. D, it's concave down, nowhere. And E, inflection points, there are no inflection points. Concavity never changes. So, so we're going to do that on, I think, the next few problems also. 16 and 17. So 16 is f of x equals x to the fourth minus 8x squared plus 16. So we need to take the derivative, 4x cubed minus 16x, set it equal to 0 undefined. Factor it, 4x, x squared minus 4. Factor it again, difference of squares, x plus 2, x minus 2. So critical points are going to be 0, 2, and negative 2. So then we're going to do a line check for f prime, label it. Put these in order, negative 2, 0 to 2. Test a point, x equals 3, positive, negative, positive, negative. I like to draw these little arrows. So it is decreasing, increasing, decreasing, increasing, relative min, right? Valley, peak, relative max, relative min, lots of good information. Critical points, stationary points, all that stuff's right there. So for part A, it says increasing, so it's increasing on, we're going to say negative 2 to 0 and 2 to infinity. B, it's decreasing on negative infinity to negative 2 and 0 to 2. Concavity, we got to take the second derivative, which would be 12x squared minus 16. Set it equal to 0 undefined. Factor it. So we take a 4 out. I mean, you could solve this. I mean, you could do a whole difference of squares, but you could also do x squared equals 4/3, square root of both sides, plus or minus 2 over root 3. These are your critical points. So we're going to do a line check, f double prime. And so we have negative. I mean, you could leave it square root of 4/3, or you could do 2 over root 3, or you could even do 2 root 3 over 3. Whatever. Test a value. I'm pick 0 here. I feel like 0 is an easy one, that's for sure, in between these. Then I don't have to estimate these. So if I put 0 in the second derivative, it's going to be negative, positive, positive, concave up, concave down, concave up. Inflection points. We have all of our answers on this picture. We just have to write them down now. So C is concave up on negative infinity to negative square root of 4/3 and square root of 4/3 to positive infinity. D concave down on negative square root of 4/3 to positive square root of 4/3. Do not include the endpoints. E inflection points at x equals negative square root of 4/3 and positive square root of 4/3. Okay, 17, similar problem. F of x equals x squared over x squared plus 1. We need to do first derivative. This is going to be low d high minus high d low all over low squared. Clean it up. It's going to be 2x cubed plus 4x minus 2x cubed. I'm going to leave the bottom factored, which is going to give us 4x over x squared plus 2 squared. So we're going to set that equal to 0 undefined to find critical points. So we get one from the top, x equals 0, but when you set this equal to 0 on the bottom, you get imaginary, which we're not going to put on graphs, but I still need to see the work for it. So this is our only critical point. So we're going to do a line check, put 0 on there, test a point, x equals 1, positive, negative, little arrows for the slopes, decreasing, increasing, critical point, stationary point, relative, min, lots of good stuff. So A says, where is it increasing? So it's increasing on 0 to positive infinity, include the 0. B, decreasing on negative infinity to 0. Okay, so then we need the second derivative. Now, so we could do quotient rule again. Low d high minus high d low. Now d low, you have a chain rule here all over low squared. That's kind of messy. Probably try to clean it up. Oof. I mean, well, let's start factoring it because I think that might be easier. I see an x squared plus 2 in both of these terms, right? But this one has another one, so it's going to be 4x squared plus 8. And then this one is going to be 2x squared. It's going to be 16x squared left over. So I'm just trying to be smart here. So what do we get? We get negative 12x squared plus 8 over x squared plus 2 cubed. It's your second derivative. Ugh. So equal to 0 undefined. So the top is going to be x squared equals 8/12 or 2/3. We're going to take a square root of both sides, plus or minus. So x equals plus or minus square root of 2/3. Those are your critical points. The bottom, you're going to get x equals plus or minus I root 2. So we're going to get rid of those. So we're going to do a line check for the second derivative. So we have negative square root of 2/3 and positive square root of 2/3. And we're going to test a point. X equals 0 seems attractive to me. And that's going to be positive, negative, negative. So it's concave down, up, down, concave down, concave up, concave down. And these are for sure inflection points. So let's see. So I'm going to say part C, concave up on negative square root of 2/3 to positive square root of 2/3. D, concave down on negative infinity and negative square root of 2/3 and square root of 2/3 to positive infinity. Okay, now let's see. Okay. 21. Now this is on page 306, and the directions, this is 21, 22, and 24. So 21, what they say is find the relative extrema, that'd be relative maxes and mins using both the first and second derivative tests. So you don't need to worry about the second derivative test yet. But essentially, it's all the work we've been doing so far in this assignment on the last several problems. So they give you a function. You want to take the derivative, set equal to 0 undefined, and find critical points. So you could, factor it if you want. And we get x equals -2 as a critical point. And then you do a line check. You put this on there. You test a point. Tell me what you test. I'm going to put 0 in here. It's going to be negative. Test it in the derivative. Okay, label it derivative. Negative, positive. Okay, so increasing, decreasing, critical point, stationary point. But look, that's a relative max. And that's what you're looking for on this. You're looking for relative extrema. So this says, so what we could say is we could say, now we don't actually know what the relative max is right now. This is where it's at. But to get the relative max, you have to plug this value into the original function to get the y value of the original function. So if we plug that in and simplify, we get 1 plus 8 minus 4. 9 minus 4 is 5. So the relative maximum is 5 at x equals -2. Now, how do you justify that? And this is something we're going to go over more soon by the first derivative test. That's what this is. That's what we're using, the first derivative test for relative extrema. And well, how do you know? Like, okay, that's the name of it. Since it went from up to down, essentially, we know that's a peak because it went up and then it went down. So how do you write that in more technical terms? Since f prime of x was positive on x less than -2, and f prime of x was negative on the right side, which is when x is greater than -2. So this would be the most thorough, justified answer. 22, same kind of thing. F of x equals 2x cubed minus 9x squared plus 12x. Gotta take the derivative. It's gonna be 6x squared minus 18x plus 12. I'm gonna set equal to 0 undefined. We should factor it. So I think we take a 6 out of all that stuff. That would make it easier. 3x plus 2. And then let's see if we can factor this x minus 1 minus 2. Perfect. So x equals 1 and 2 are your critical points. So then we're going to do a line check. 1, 2, test a point. X equals 3. Everything's positive, negative, positive, up, down, up, increasing, decreasing, increasing. Relative max right there, right? Relative min there. You can see it, high point, a low point. Now, to get the actual values, you plug these back into the original. If you plug 1 in, you get 2 times 1 cubed minus 9 times 1 squared plus 12 times 1, which would be -7. That would be 5. And if you plug 2 in, it's a little harder because it's going to be 2 times 8 minus 9 times 4 plus 12 times 2. So that's going to be negative 36 plus 16 is negative 20 plus 24 is 4. So the relative maximum is 5 at x equals 1 by the first derivative test. For relative extrema, since f prime of x was positive on negative infinity to 1, and f prime of x was negative on 1 to 2. So that's a really good thorough answer for the relative maximum. And then you could do the same thing for the relative minimum. The relative minimum is 4 at x equals 2 by the first derivative test for relative extrema, since f prime of x was negative on the left on 1 to 2, and f prime of x was positive on the right, 2 to positive infinity. Yeah, justification, hard stuff. And then 24. Get some trig in here. Trig never goes away. Now the only one answers from 0 to 2 pi. It doesn't look like it should include the endpoints though. So we got to take the derivative. F prime equals 1/2 plus cosine x equals 0 undefined. So cosine x equals negative 1/2. Alpha equals cosine 1 root 3 2 root 2 over 2 1/2. Pi over 6, pi over 4, pi over 3. Quadrants 2 and 3 is where it's negative. So x equals 2 pi over 3 plus 2 pi k. And x equals 4 pi over 3 plus 2 pi k. We only want the answers from 0 to 2 pi, so that's going to be 2/3, 2 pi over 3, and 4 pi over 3. So these are your critical points. So then you do a line check. Zero to 2 pi. Test point. I like 0 for trig. Plug it into the derivative. Cosine 0 is one is positive. It's positive, negative, positive. Increasing, decreasing, increasing. So we have a relative max right there and a relative min right there. You can see it. It's easy. You can see it. Now the justification isn't super fun. Plus, if we want the actual values, we're going to have to plug these back into the original function. So if you plug 2 pi over 3 in, you're going to get pi over 3 plus sine of 2 pi over 3, which is going to be pi over 3 plus reference angle is pi over 3 for sine. That's going to be root 3 over 2. And then 4 pi over 3 is going to be 2 pi over 3 plus sine of 4 pi over 3. So it's going to be 2 pi over 3 minus root 3 over 2 because it's in quadrant 3. And then we just got to write the answers. So the relative maximum, I'm just writing smaller and smaller fast space, rolling back to maximum is pi over 3 plus root 3 over 2 at x equals 2 pi over 3 by the first derivative test for relative extrema. That's the name of it. That's part of your justification. Since f prime of x was positive on the interval of 0 to 2 pi over 3, and f prime of x was negative on the interval to the right of it, which was 2 pi over 3 to 4 pi over 3. So that's the justification of relative max. The relative minimum is 2 pi over 3 minus root 3 over 2 at x equals 4 pi over 3 by the first derivative test for relative extrema, since f prime of x was negative on the left, less than 0, on 2 pi over 3 to 4 pi over 3, and f prime of x is positive on the right, 4 pi over 3 to 2 pi. Wow. And that they actually directions told you to do about the second derivative test too, which I'm not even getting into. I haven't showed you guys how to do it, but this is the answers. These are justifications. This is the work. The work is like the work from these other problems. You do first derivative test. You just you take the first derivative, set it equal 0 and define critical points. Put on line check, do line check, and it's all right in front of you now. And writing the answers is a bit more work. So, anyways, there you go.